So now we're going to turn our attention to parallel fluxes. What is a parallel flux and how can you use it? So we'll start out by talking about the capabilities of a parallel flux class. The main idea of parallel flux is to try to simplify parallel processing relative to the alternative way of doing processing with concurrent operations, which is the flatMap concurrency idiom. So here's the flatMap concurrency idiom, which is doable but a little bit wonky and get carpal tunnel syndrome from having to type extra code. And here's the parallel flux way of doing things, which if you have the right kind of problem, a problem that's embarrassingly parallel, decomposes very nicely onto these features. So parallel flux is necessary because the flatMap idiom performs well, but it's a little bit convoluted. So here's an example where we're going to take an array of big fractions, turn it into a flux, and then we'll use the flatMap concurrency idiom to say, for each big fraction in this flux, go ahead and take each one, emit it from a callable, and go ahead and multiply these things together and do the computations, and then add all the results up. So a little bit more trouble than you might want to have. What we're trying to do here is get a streamlined set of parallel computations that look very much like what Java Streams does. Java Streams is very, very concise when it comes to doing parallel processing. You say, convert the big fraction array into a stream, make that a parallel stream, multiply each thing together, and reduce the results. So it's much cleaner to read that, I would argue, than to read this. So parallel flux is also a subset of flux, meaning that it doesn't support all the operations that flux has. It just has some of them. And it allows you to be able to do these parallel computations using this concept called a rail. Like I said, it's very similar to Java parallel streams, and they're both intended for embarrassingly parallel tasks, as is the flatMap concurrency idiom for that matter. So recall that an embarrassingly parallel task is one where there's little or usually no dependencies between the tasks, so they can each run in parallel on separate cores without having to worry about any contention for shared resources. And it avoids the convoluted syntax of the flatMap concurrency idiom. So rather than doing this, it does something that's a little bit more straightforward. Now, how do you get a parallel flux? Well, you take a regular non-parallel flux, and you call the parallel factory method that's defined on it. And you give it the level of parallelism that you want. And so what happens here is it goes ahead and it takes each item and it gives them off to something it calls rails, which are just basically the threads or the cores that are processing, threads running on cores. And it processes the things in round-robin order. By default, the number of rails is set to be the number of available CPU cores, which is what you'd pretty much expect. And you can change this setting programmatically by passing in a parallelism count that's either greater or less than the number of cores. But it's usually not a bad idea just to stick with the one that comes out of the box. So let's talk a little bit about the key operators that are found in the parallel flux class. They're a subset of the flux operators. And we have things like map, filter, concat map, flatMap, collect, reduce, and so on. So those are some of the things that you can do. Now, it turns out that some of these things are not as useful as you might like. In particular, collect is kind of wonky with a parallel flux. So you usually have to do something else, which we'll talk about in a second. There's another operator that parallel flux has that doesn't come from flux called run-on. And run-on specifies where each of the rails will wait and do the processing on the elements that are sent to it in round-robin order. And when you call run-on, you give it a scheduler, and this scheduler does not perform work stealing for whatever reason. What's returned is a new parallel flux instance that will run its elements on that scheduler. And the typical schedulers are the parallel scheduler, which we've talked about before, and the bounded elastic scheduler, which we'll talk about next. You can convert a parallel flux back into a flux using the sequential operation. And the most common reason to do this is there are a lot of operations on flux that don't appear on parallel flux. So often you'll run everything in parallel to a point where you can't make any more progress with parallel flux operators, and then you turn it back into sequential flux, and then you finish up whatever you have left to do. And this merges the values from each of the rails in a round-robin fashion. You could also call reduce on a parallel flux to convert all the different rail values into a single mono. And this is how you do it. You call reduce. Reduce is passed a by function that reduces two values into one successively. And you get back a single mono that emits either the reduced value, if that's what you ended up with, or if the parallel flux was empty, you'll get back an empty mono. So here's an example which we're going to look at in a second when we talk about the case study, where we're going to multiply an array of big fraction objects in parallel using parallel flux operators. So you see we take the big fraction array, we turn it into a parallel flux, we run that on the computation scheduler. For every one of these big fractions, we multiply it by some constant. We reduce everything together into a single result by adding up all the results, and then we display the results and we return an empty mono to synchronize with the async task barrier or whatever's waiting for us at the end of all this. So that's the end of the overview of the parallel flux class.